Are you following?
Yes, sir.
Okay. So, so much we discussed in the last class. Okay. Now we'll start the next part of this. This we discussed in the last class. We obtained the coordinates. Okay. How does the coordinates of an observer O prime or S prime look in the frame S, right, in the XCT plane? Okay. This has been asked, right? This angle and this angle are the same. Okay. So this this CT prime axis has an angle alpha with respect to CT, whereas this X prime axis has the same angle alpha, but with respect to X axis. Okay, that's what we understand from these things. Right. So you remember here that, so I want you to just notice the fact that this is a world line, all right? This is the world line of the observer. Okay. And for him, you see that X by CT is equal to V by C, or X by T is equal to V. Okay. Here, along this line, the slope of this line alone is X by T equal to V. But if you take this line, right, if you take this one, you see that it's CT by X equal to T by X, CT by X equal to tan H phi is V by C, am I right? Okay. So you see that over here, T by X is not equal to V. All right. Along this line, T by X is not equal to V. You have to remember this. All right. It looks just the opposite. It's CT by X equal to V by C. All right. Or T by X is equal to, what do you say? Yeah, T by X equal to V by C square. Am I right? Oh. CT by, just give me a moment. We said along this line, CT prime equal to 0, CT by X equal to V by C, that's correct. All right. So along this line, when you see CT T by X, you shouldn't put 1 by V. All right. Okay. So along this line, X by T is not equal to V. All right. X by T is not equal to V. So whenever you see X by T is X by T, you cannot simply put V. All right. That's true only for the world line. Right. Along this line, it's different. Okay. So we know the slope of these lines. It's fine. CT by X equal to V by C. Right. Okay. Now the same question can be asked. So we can talk about the viewpoint of the observer O bar or S bar, okay, however we call it. So when you look from the framework of S bar, right, when you look at the frame of S bar, you will see that the frame S moves in minus X direction, with velocity V. Am I right? Okay, we said that S bar moves in the positive X direction with velocity V with respect to S. But if you look from the frame S bar, you'll see that S is moving in the minus X direction with velocity V. Am I right? Yes?
Yes.
All right. So if that's clear, now we can now talk about the viewpoint of S bar. We can write the coordinates as CT prime and X prime. Okay. So now these are the coordinates of S prime. All right. These are the coordinates of S prime. So he will see that this we can also extend this. So according to S prime, right? According to S prime, S is moving in the minus X direction with velocity V, or it's moving at the velocity minus V, so to speak. All right. So in that case, you'll see that we can use the same arguments and see that it's symmetrical, right? This would be CT and that would be X. All right. So this is the viewpoint of S prime. So you see that they are scissored together. All right. So if you look at a moving observer and draw his coordinates in your frame, you'll see that they get scissored together. Okay. It's so this is kind of rotation between space and time, but it's different. All right. The sense, the orthogonality is different when we talk in Euclidean space and Minkowski space. Okay. So this can be asked. It's a good thing to understand this. So it's so much clear. Right. Now it's very easy to look at. So if so much is clear, it's very easy to understand the basic effects of special relativity like time dilation. Okay, we already discussed this, right? Time dilation we already discussed in that problem of twin paradox. Okay, now we can also talk about length. Okay, let's talk about loss of simultaneity. Loss of. So we have already seen that according to Lorentz transformations, we have already seen from a different viewpoint that simultaneity is not absolute, right? Two events which are simultaneous for one observer need not be simultaneous for another observer, right? So let's just look at it from using space-time diagrams. So we have got CT, we have got X. Okay, now we can see if you look at this, this is the, let's say this is the viewpoint of observer S. Okay, this is the viewpoint of observer S, the coordinates of observer S. Okay? So you see that two events happening along this line are simultaneous. All right, so if you take a line parallel to the x-axis here, these events are all simultaneous. Am I right? Okay, so these events happening in the same line or parallel to x-axis happen at the same time. Okay, let's say this is T0, T1, T2. Okay, so these events happen at the same time because this line corresponds to Ct equal to a constant, all right, or time is equal to a constant. Am I right? This line corresponds to time equal to 0. This is just the x-axis. So these events happening, if they fall in a line which is parallel to the x-axis, we say that these are simultaneous. Okay, this is fine. But if you look at the viewpoint of S prime, if you look at the viewpoint of S prime, his x prime axis goes like that. Okay, his x prime axis goes like that. All right. So you see that for this observer S prime, only the events parallel to his x prime axis are simultaneous. Okay, right. So if you draw lines parallel to the x prime axis, all events lying on these lines are simultaneous for the S prime observer. Okay, so you see that these two events are simultaneous for S observer, but they are not simultaneous for S prime observer. Right, you see that they are not simultaneous for S prime observer. Okay, so these two events are simultaneous for S prime observer because they lie on the x prime axis. Okay, but if you look at what do you say, the S axis, you will see that. Let me call this event A and event B. Okay, so we can, I'll just give you an example. A and B are simultaneous. In which frame? S or S prime? A and B. A and B are simultaneous in
X prime.
S prime, is in S prime. Okay, but you will see that their time order is not preserved. If you look at in S, you will see that A happened before B. Am I right? A happened before B because A happened at, let's say, time T1 and B happened at time T2. Okay. Similarly, if you look at these two events, okay, these two events, you will see that these events are simultaneous in S frame. Let's write this as C and D. Okay, C, D are simultaneous in S frame. Am I right? Okay, but you'll see that if you draw lines parallel to this, you will see that D happened before C in S prime. Okay, D happens before C in S prime. Is this clear? Because this is the time axis, right? This is the x prime axis. So you see that D happens at an earlier time and C happens at a later time. All right. So these are examples for space-like separated events. All right. These are examples for space-like separated events. Okay? These events are space-like separated, which means that the time order need not be preserved. The time order need not be preserved. All right. One observer will say that they are simultaneous. Another observer will say that C happened before D. Another observer will say that D happened before C. Okay, there will be an observer who says that D happened before C, and there will be an observer who says that C happened before D, and there will be another observer who says that C and D are simultaneous. Okay, this is clear?
Yes, sir.
Okay. So this is a very interesting way to look at this. Okay, I think we should. So again, if you look at time-like separated events, okay, xct, you look at two time-like separated events. Okay, if you look at two time-like separated events, there is no frame in which these are simultaneous. Okay, the time order is preserved. So if this is B and this is A, every observer will agree that B happened after A because it's time-like separated events. Okay, because the fastest observer can only move slightly less than the speed of light. Okay, speed of light goes at 45 degrees. Okay, so every observer, this is the fastest observer. Okay, so this observer will also say that A happened before B. Right, this observer will also say that A happened before B. This time ordering cannot be reversed if they are time-like separated. Right? Time ordering cannot be reversed if they are time-like separated. So, for example, every observer will agree that you were born after your mother. Right? No observer will say that you were born before your mother. All right. So, if you have a daughter and mother, okay, every observer will agree that daughter was born after mother was born, for example. All right. These are causally connected events. Okay. All right. Now we can also, if that's clear, we can move on to the next thing, length contraction. We can look at length contraction from the geometric point of view. Okay. So again, we'll draw this axis for the time being. If you have any, if you need any clarification, you can ask, but don't worry. These concepts we are only briefly discussing. Okay. These are useful to solve problems sometimes in much easier way. You'll see that the kind of thing that we are building up here will help us solve problems in a very easy manner. Okay. So if you have any questions, you can just ask. We can discuss. Okay. No problem. So suppose this is the frame S. All right. And let's say there's a rod of length L, let's call it as L, okay, or L0 for length, okay, at rest in a frame S, frame S, okay. Let's say that there's a rod of length L0 at rest in frame S, okay. So for simplicity, we'll also imagine that one of the ends is coinciding with the origin, okay. So, okay, this is the length L0. So there's a rod at rest in your frame. No problem. You measure its length, it's equal to L0. Okay. But what about another observer S prime who is moving at a velocity V with respect to this? Right. For him, you'll see. So you can also draw the world line. You see that every object has a trajectory in space-time. If it's at rest, it's just a straight line. Right. So this is the world line of this coincides with the world line of the rear end or the back end. Okay, and the world line of the front end in the frame S prime. Okay, this looks like this. It's a straight line parallel to the time axis. This is the world line of the front end of the rod. Is this clear? Now you can also draw the coordinates of S prime. Okay, the coordinates of S prime. Let me say that he's moving at a very high speed. Okay, so we'll. I think I should. Should I draw dashed lines? I think I'll. This is CT prime. Sorry. CT prime. Okay. And we've got X prime. Okay. So this is the world length. Okay. Now, what's the question is? So I've drawn the new coordinates as we discussed. Okay. What is the length? Let's say L measured in frame S prime. All right. So you have to be careful here because in the frame S prime, the length is moving. Right. The length is actually moving. Am I right? In the frame S prime, he's measuring the moving length. All right. So he has to be careful to take the. So if you have a moving scale, all right, you can measure the length as x2 minus x1. It's fine, but you have to be careful to take these endpoints simultaneously, right? Take endpoints simultaneously. Am I right? Otherwise, if you take x1 coordinate at time t1 and the rod has moved to here, and then if you take x2, then x2 minus x1 is not the length. Am I right? If you take these coordinates, the coordinates of the endpoints at different times, okay, for a moving length, then it's not the length, right? If you need to get the length, you have to take the coordinates simultaneously, right? You have to take x1 and x2 simultaneously. Okay, if it has moved by a distance, then you get a different length. It's not the length of the rod. Am I right? So this observer, S prime observer, has to take this length simultaneously, right? And for the S prime observer, the line of simultaneity is this. Okay, all the events along X prime axis, these are simultaneous. Okay, so he says that this is the rear end. He took the rear end and the front end, the coordinates simultaneously. Okay, so for him, this is the length. This is clear because he has to take them simultaneously. So clearly, you see that what two observer call as length are different things. Okay, so the S observer calls this distance as length, whereas S prime observer calls this distance as length. Is this clear? So obviously they are supposed to be different. All right. Now you have to remember that CTX has a Euclidean geometry. No, so it has a Minkowski geometry. So you can use the generalization of Pythagoras theorem. All right. This would be delta. Let's say this is CT. So we are talking about straight lines. Okay. This distance is CT. This distance is L0. Okay. So we can say this is just the generalization of Pythagoras theorem. Right. If it was Euclidean geometry, we could say that L square is equal to L0 square plus C square T square. All right. Am I right? If it was Euclidean geometry, we could say that L square is equal to L0 square plus C square T square. Okay, this is for Euclidean, but we know that we don't have Euclidean geometry, so we will have to use the Minkowski generalization of this. We have to say that L square is equal to L0 square minus C square T square. Okay, this minus signs defines the geometry. Am I right? Is this clear? Okay, so this is the generalization of what do you say, the Pythagoras theorem in space-time, okay, or in Minkowski geometry. Or if you are interested, you can write. If you are interested, you can just construct the invariant quantity. If this is not really intuitive, we can construct the invariant quantity in both frames. We know that L. Okay, we are looking at the space-time separation between these 2 points. Okay, so we can say that L square minus C square T prime square is equal to L0 square minus C square T square, because this is invariant. Am I right? This combination is invariant. This is what we have been discussing so far. Okay? Whether it's a minus sign here and a plus here, or minus here and plus here, it's the same thing. Okay? Both these are invariant. Okay? But we said that we are taking this endpoint simultaneously. So T prime is equal to 0. Okay? The separation between time separation between these two events, the time separation between these two events in the S prime frame is 0. So we get this same equation. We see that L square is equal to L0 square minus C square T square. Is this clear? We have just used the geometry. Okay. Now this can be simplified in this way. You can take L0 outside. Okay, this is 1 minus C square T square by L0 square. Okay, C square T square by L0 square. Okay, and what is C square T square by L0 square along this line? Okay, for this line, we are not talking about the world line, we are talking about the X prime axis. What we already know the slope for this, right? We know the slope of this. C square T square by L0 square is V by C. All right, CT by L0. We already saw that. CT by L0, the slope of this line, we have already discussed this. CT by L0 is equal to V divided by C. We already discussed this just before some time. Okay. So using that idea, you see that this is equal to L0 square, 1 minus, okay, CT by L0 is V by C. So this is V square by C square. Okay. Or this means that L is equal to L0 square root of 1 minus V square by C square. We got the familiar equation for length contraction. Okay. But the idea is very clear here. The basic premise that we start with is that if you need to measure the length, you have to take the coordinates simultaneously. Okay, but for different observers, simultaneity is different, right? So that's the reason why we have a length contraction. S says that, so according to S, if you look at the S observer at S, if you look at the observer S, he will say that, all right, this person is making a mistake because he did not take it simultaneously, because these two events, let's say E1 and E2, are not simultaneous for S. Okay, so this S will say, explain the result. He'll say that, all right, the other observer did not take this endpoint and the rear, so the endpoints, the coordinates of the endpoint simultaneously. That's why he got a different length. I mean, this is one way to explain it from the viewpoint of observer S. Okay, this is fine.
Yes.
All right. Okay, now I think that that's enough from the geometric diagram thing. All right. Now, and there is another important concept called four vectors. Okay, we need to go into four vectors. Okay. So from the geometry thing, I think that's enough. We have been very brief, but I think that is sufficient. Now we'll go to four vectors. All right, I'll tell you why four vectors are important. Okay, you may have problems using collisions, all right, to find the momentum or energy, okay, using conservation of energy, momentum, etc. Right? So such problems have been asked. So they'll say that a muon and a pion have, for example, collided. They are having a collision, and what's the momentum afterwards in terms of the initial energy, for example? This kinds of question can go. What's the final mass of the particle? Okay, these questions can be asked, and usually, if you are familiar with four vectors, you can easily solve the problem. Okay, there are different ways to manipulate this. There are certain invariant quantities. We can construct this and solve the problems easily. Okay, in any way, these four vectors are important in special theory of relativity. So what do we mean by four vectors? So we'll first discuss what we mean by vectors or three vectors we are familiar with. Okay, so the first thing you have to understand and then later forget is the idea that vectors are actually invariant. Vectors are geometric objects and they are invariant. You have to understand this. These are geometric objects. They have a definite geometric meaning. They are invariant under coordinate transforms. So now I'm talking about the usual vectors that we have discussed. Okay, so for example, if you take the length, the position vector of an object, okay, from the origin xy, okay, we are talking about the usual vectors. This is r vector. Okay, so this actually corresponds to a specific point in space, and this is invariant, right? It always you can discuss it from a different frame. Okay, and the components of this vector will be different, but you will see that the vector itself is invariant because you are talking about an object in space. Okay, so we are talking about three vectors. How do we define vectors? All right, how do we define vectors? What's the definition of a vector? What's the definition of a vector? Okay, so the usual definition that we
The
learned,
direction of.
yeah, something has a direction and a magnitude, right? This is the usual definition, but we need a more rigorous definition here. Okay, I'll explain why. So we know that if you take a vector r vector, just as an example, it can be written as xi plus yj plus zk. Okay. Now you can rotate this vector. You can rotate this vector and write the same vector as r vector is equal to x prime I prime plus y prime j prime plus z prime k prime. Okay. Now I'll just give you the idea that this vector itself is invariant, all right, because the components have changed and the basis vectors also have changed. Okay. X, y, z are called the components. X, y, z are called the components of the vector, and these components are dependent on the coordinate system that you choose. So, right, if this is the coordinate system you choose, then the x component this length and y component this length. And if you take some other frame, right, the x component and y component will be different. Right? So the x, y, z components, these are components, and I, j, k are known as the basis vectors. Okay, but for all practical purposes, okay, for all practical purposes, what we do is that we can call, for all practical purposes, we can call x comma y comma z as the components. We can call the components as vectors. Okay, so all practical purposes, you can take three numbers x, y, z and call it a vector. You can call it a vector, no problem. Okay, but you have to remember that actual vector is a geometric object like this. It's invariant, but the components of a vector transform when you make a coordinate transformation. Right, but in special relativity especially, there is no problem in calling these components itself as a vector. Okay, but you have to remember these are only components of a vector. And how do we define a vector? A vector can be defined, okay, by the transformation properties of their components. Okay, so how do we define a vector? We define a vector by the transformation property of their components. You ask the following question: how do the components change under a coordinate transformation? Right, and if it obeys a certain way of transformation, we say that these components or these numbers form the components of a vector. We'll just develop it like this. Okay, if, for example, we'll take rotation as an example for the coordinate transformation. If the components of or we'll say like this, if three numbers transform in a particular way, let's say under rotation, then we can say that they form the components of a vector. Okay, so so far I have been careful to make a distinction between components and the vector itself. Okay, but as I said, for all practical purposes, hereafter we'll call the components itself as vectors. Okay, this can be done. Okay, we can do all mathematical manipulations without worrying about the basis vectors. If you have the components, you can do everything. All right, we'll call components as vectors, but you have to remember that inside your mind, you have to remember that vectors are geometric quantities which are invariant. But for practical purposes, we can always take these components and call them as vectors. All right, for all mathematical manipulations, it doesn't make any change. Okay, so I'll just since we have agreed to use it like this, we can say that vector, okay, a three vector, for example, we'll call it a vector. All right, vector is a collection in 3 dimensions. All right, let's say a vector in 3 dimensions. We are calling about we'll call it a 3 vector if you like. Okay, because it has 3 components. A 3 vector is a collection of 3 numbers. It's just a collection of 3 numbers. Okay, which transform in a specific way under rotations. Okay, under rotations. Is this definition fine? Do you agree with this definition? Okay, so for example, if we know that under rotation, an example is that under rotation about the z-axis, okay, under rotation about z-axis, we can write this as the transformed coordinate as x prime is equal to x cos theta plus y sin theta. Okay, y prime equal to minus x sin theta plus y cos theta. You might be familiar with this rotation thing, and z prime is equal to z. This is a rotation about z axis. This is a rotation about the z axis. Okay, now we can write this in a matrix form. We can write this in a matrix form. We just make a new notation. All right, we'll call x prime. Sorry, we'll call x as x1 and y as, what do we call it? We'll call it as x2 and z as x3. Okay. Now, if you write it like that, we can write this in the matrix form. We'll write it as column. This three numbers we'll write as a column matrix: x1 prime, x2 prime, x3 prime. Okay, is equal to, we have got cos theta, sin theta 0, minus sin theta, cos theta 0. Okay, 0, 0, 1. x1, y1, and sorry, x1, x2, and x2. So we have written it as a matrix. That's all. Right, so if you see that x1 prime is equal to x1 cos theta plus x2 sin theta, as we have here. Okay, and x2 prime is equal to minus x1 sin theta plus minus x1 sin theta here. Okay, plus x2 cos theta. That's also fine. And you see that z prime is equal to z. Z prime, x3 prime is equal to this 0, 0, and x3. All right. So this is an example for a rotation. Okay. Now you can construct any rotation matrix like this. You can construct a rotation about y-axis or x-axis, and you can construct a rotation about any arbitrary axis. But the basic idea is that the components of a vector transform according to this. We can say this is just the position vector. Okay, this is just the components of a position vector, right? R vector equal to xi plus yj plus zk. Okay, so we can just write it in this form. The rotation matrix could be a general matrix, but it has to be a rotation matrix. Okay, the rotation matrix has properties. So we can write this like this. Okay, xi prime, this is a notation I'm using, is equal to, I'm writing it as a matrix multiplication, r I prime j xj. This matrix multiplication I'm writing in this. Okay, xi prime is equal to r I prime j xj. All right. So here I'm using Einstein summation convention. There's a summation over j. J is summed over. Okay. So this is a matrix multiplication. If you're familiar with this, is a matrix multiplication. Okay. So this, if for example, if you want x1 prime, okay. For example, if you want x1 prime, what you will do is that you put here it's 1 prime, so you write it as r 1 prime j. Okay, j, there's j, so I have to sum over all these three quantities. Okay, j is so if sum over it's 1 x1 plus r 1 prime, this is fixed by this. Okay, and 2 x2 plus r 1 prime 3 x3. This is what I mean by this. Okay, now you just take these components. I'm naming these components like this. This is r1 prime 1. This is r1 prime 2. This is r1 prime 3. Okay, this prime I'm just putting so that this is consistent. All right, the prime coordinates means that it's a new coordinate system. And this would be r1 prime, so r2 prime 1, r2 prime 2, r2 prime 3. Okay, and this would be r3 prime 1, r3 prime 2, r3 prime 3. Okay, this primed means we are, so I'm using it here to show that this matrix actually connects the old coordinates and the new coordinates. All right, so that's why I put one index as I prime and the other one as j. Okay, is this fine? So this is how the position vector transforms. The position vector transforms in this form. Okay, xi prime is equal to ri prime j xj. Okay, this is the transformation of position vector under rotations. Okay, so I'm just writing it in a slightly more abstract form. Now I define a vector. Okay, now I define a vector. Now I define a vector. Definition of a vector is this. A vector is a collection of three numbers which transform like, just like, or exactly, okay, exactly like the three coordinates, okay, or we can say exactly like the components of position vector under rotations. Okay, so this is the definition of a vector, right? What's the definition of vector? We know that the position vector, components of a position vector transforms according to this rule, right? And how do you define a three vector? A three vector is a collection of three numbers, okay, provided they transform exactly according to this equation under rotation. That means we can say that, for example, A1, A2, A3 form a vector. Okay, these three numbers A1, A2, A3 form a vector. Okay, form a vector if they transform under rotations as, okay, we can write it like this: AI prime is equal to Ri prime j, the same rotation matrix Aj. Okay, summation over j is implied. Okay, now this is the definition of a three vector. Okay, is this fine? Now this is a more rigorous definition for a three vector. Okay, again, I am not talking about the basis. Okay, we are using the same word vector for its components. All right, or we are calling the components as the vector. Okay, this can be done. Is this fine? Is this the definition of a vector? Three vector. Okay. Shall we move on to four vectors?
Yes, sir.
Right. Now we can discuss four vectors. Okay, so we are defining four vectors. So here the three vectors are defined by the rotation matrix. Okay, here it will be the Lorentz transformation matrix. That's all. Lorentz transformation matrix. All right. So we have already seen that under the Lorentz transformation, we can write it in terms of sine or in terms of what do you say, the hyperbolic cosine and hyperbolic sine. We have seen that Ct prime is equal to just a second. Ct prime equal to Ct cos phi minus x sine phi, and x prime is equal to minus Ct sine h phi plus x cos h phi. Again, we can write it as and we can write y prime is equal to y and z prime is equal to z. Okay, again we will write it as a matrix. We don't want the details of the matrix, but we know that this can be written as a matrix. Right? Now again we write the new notation. We'll write Ct prime as x0. Okay, because we have four coordinates here. We have got four coordinates here: 1, 2, 3, 4. Okay, so the time component we always write it by x0. In some textbook they write it as x4, but we don't use it anymore. The time component is always mostly written as the zeroth component. Okay, and we'll write x prime, sorry, Ct as x0 and x as x1, y as x2, and z as x3. Then just like in the case of the rotation, we can write the transformation and the Lorentz transformation as, we'll write it as x mu prime. Okay, so we are using Greek indices here for mu is equal to 0, 1, 2, 3. It can take four values, all right? And we use Latin indices, I, j, k, etc. It takes only 1, 2, 3. Right? This is the convention that we are using, right? If you use a Latin index, it takes values only 1, 2, 3. Whereas if you use the Greek index, it takes values 0, 1, 2, 3. Okay, is this fine? So we can write this equation like this. This x mu prime is equal to, we have got Lorentz transformation matrix. We'll write as lambda mu prime nu x nu. Okay. This is I am just writing this in the matrix form. The components of the matrix, it depends. All right. If it's boost about x-axis, we'll have a, but the important thing is that there is a Lorentz transformation matrix. This is known as a Lorentz transformation matrix. Okay. Now this is just like the rotation matrix. It's similar. It actually rotates between the time component and the space component in a way. All right. So this is the Lorentz transformation matrix. All right. So this is how the coordinates transform. This is the coordinate transformation under Lorentz transformation. Now we are ready to define a 4 vector. Okay, we can 4 vector. A 4 vector is a collection of how many numbers? 4 numbers. Okay, 3 vector was a collection of 3 numbers which transformed like the coordinates, but here we have 4 numbers. Okay, which transform. We can write this as equation 1. Okay, transform exactly like equation 1 under Lorentz transformations. Okay, this is the definition of a 4 vector. Again, we are talking only about the components. You have to keep in mind that a 4 vector itself is a relativistically invariant object. All right, this is geometric. It has a specific geometric meaning, but the components transform. We are defining vectors in terms of the transformation of their components. Okay, so we can say that a collection of 4 numbers a0, a1, a2, a3. Okay, a collection of 4 numbers form a vector if they transform under Lorentz transformation as, okay, a mu prime is equal to lambda mu prime nu a nu. Okay, so this is it. This is the 4 vector. Okay, again there's a summation over nu. It's implied. The summation over nu will run from, you have to sum over 0, 1, 2, and 3. Okay, and this is a matrix. Remember that this is a matrix. It's known as the Lorentz transformation matrix. So is the definition of a 4 vector clear? Yeah.
Yes, sir.
Right. Now we can go to the idea of a scalar product. We can go to the idea of a scalar product. Okay. So in 3, again, we'll discuss about 3 vectors first. We know that, so how do you measure the length? You know that length is invariant under rotation. Length of an object does not change when you change the coordinate system. If you rotate the coordinate system, am I right? So we have got 3 vectors. We know how they transform under rotations, and we know that length. So length is an example of, actually, if you take r vector is equal to xi plus yj plus zk. We have defined r dot r like this, right? X square plus y square plus z square. Am I right? And if you take the square root of this, you get the length of the object, right? This is square root of, so the length of the object can be written as, we write it usually as modulus of r, that's equal to square root of x square plus y square plus z square. So this is how we have defined the scalar product, okay? So in our notation, we can write r dot r is equal to x1 square plus x2 square plus x3 square. Okay, this is fine. Or we can write as x1 plus x2 plus x3. Now I hope this is fine. And any vector, if you have any 2 vectors, a vector dot b vector, you can write it as a1 b1 plus a2 b2 plus a3 b3. Am I right? We are just taking the components and then multiplying the first component with the first component, second component with the second component, and third component with the third component. And we know that these are invariant under rotations. All right, scalar product is invariant under rotations. Okay. Now again, there's a nice way of writing this. We can write a vector dot b vector like that. We can write it as ai bj delta ij. We can write it like that. Okay, where delta ij is the Kronecker delta. Am I right? If I equal to j, this gives you. So this is a summation over both I and j. Remember that this is a summation over both I and j. Okay, this is known as a Kronecker delta. So if you sum this up, okay, if you take I and j as 1, okay, a1 b1 delta 1 1. Okay, and if you take this j as 2, a1 b2 delta 1 2, that would be 0. So the only non-zero terms that would survive would be a1 b1 plus a2 b2 plus a3 b3. Okay, fine. Is it okay writing it like this? Because delta ij is Kronecker delta. It's 0 if I is not equal to j. It's 1 if I equal to j. All right. So in the whole summation, the only terms that will survive is when I equal to j. Okay. In this whole summation, there is summation over I and there is summation over j. In all this summation, the only terms that will survive will be for I equal to j. All other terms are 0. Okay. And this delta ij, this Kronecker delta, we can give it a nice name. We can call it as the metric of, let's say, Euclidean space. Okay, because this symbol tells us how to calculate the distance. Okay, it tells us how to calculate the scalar product. This is fine, the concept of metric. And remember, for summation, okay, I'm using a convention already. For summation, I'm using this idea. It's not just repeated index, but one index on top and one index downstairs. All right, one upstairs index and one downstairs index. So we are just refined our summation convention. Okay. Repeated indices. Okay, repeated indices. Okay, in a specific way, one upstairs and one downstairs. Okay, so you should have one upstairs index and exactly the same index on the downstairs. Then you have to sum them all. Okay, summed all. Okay, clear? Following?
Yes.
So we can write this delta ij as a matrix. Okay, delta 1 1 is 1, delta 1 2 is 0, delta 1 3 is 0, delta 2 1 is 0, delta 2 1 is 1, delta 2 3 is 0. Okay, similarly 0 0 1. We can write it like this. Okay, now we can go to scalar product of 4 vectors. We need to find the notion of scalar product of 4 vectors. Okay, but we need it to be invariant. It has to be invariant under Lorentz transformations. Right? It has to be invariant under Lorentz transformations. Okay, so let's take the simplest vector that we know, the position vector. Okay, let's take, let's say, how do you call the position vector? We can write as x mu. Okay, x mu has components. X mu has I'm just writing it in a bracket. Right, x mu has component x0, x1, x2, x3. I'll just write down x0. X0 is ct, x1, x2, x3. Okay. Now we need to find a scalar product between two vectors in such a way that it is invariant. All right. Just like we took r vector dot r vector, that's equal to x1 square plus y1 square plus x1 square plus x2 square plus x3 square, which is invariant under rotations. Here need to find a combination. Let's find, okay, for 4 vectors again, 4 vectors. I'll write just x, okay, without a vector. If there's a vector, I'll call it a 3 vector. But if there's a vector, I'll call it a 3 vector. Without a vector, it means it's a 4 vector. Okay. So the components of the 4 vector are given by x mu. Right. This is the components of the 4 vector. Is this notation fine? Okay. This can be called as a let's say the position 4 vector. Okay. 4 vector with components x mu. All right. Now we need to find a notion of x dot x, which is invariant under Lorentz transformations. All right. We could always try x0 square plus x1 square plus x2 square plus x3 square. We could try this, but we know that this is not invariant under. It's not. We could just, this is just a generalization, direct generalization of this. Okay. We know this is not invariant under Lorentz transformations, right? We already know a quantity that's invariant, all right? We can define it like this: x0 square minus x1 square minus x2 square minus x3 square. We know that this is invariant under, we have already checked, right? Because this is c square t square minus x square minus y square minus z square. We have already seen that this is invariant. Am I right? Okay. So this is how we define a scalar product, right? So similarly, we'll see that because all vectors, the components of 4 vectors, transform exactly like the components of this, we can write a 4 vector a vector dot b. This as a0 b0 minus a1 minus minus a1 square. Sorry, it's b, right? So this is a1 b1 minus a2 b2 minus a3 b3. This is how we define the forward. Now this part, right? This part you can, you know that you already see that this is actually x vector dot x vector. So this you can write it as, we can, this is another way of writing it. Okay, another way of writing it, this x0 square minus x vector dot x vector. Okay, by this, when I write a vector, I mean it's a 3 vector. Okay, you see that x1, x2, and x3 are the components of the 3 vector. And if you take x dot x, you know that you'll get x1 square plus x2 square plus x3 square. Okay, this is one way of writing it. Okay, similarly, you can write this as a0 b0 minus a vector dot b vector. Okay, I'm writing this vector sign here for 3 vectors. Okay, this is how we define a scalar product of 2 4 vectors. Product of 4 vectors. Okay, fine. Okay. Now for 3 vectors we wrote a vector dot b vector is equal to ai bj delta ij. Okay, we would like to write it exactly in the same form. We need to write, okay, I'm writing now 4 vectors. There's no vector sign here. We would like to write it as a mu b mu, and we call this as the metric of Euclidean space, right? And we'll write similarly, instead of delta ij, we need to invent a new thing, eta mu nu. Okay, now this thing we'll call it as the metric of Minkowski space, metric of the Minkowski space. Metric of Minkowski space. Okay, now if you want to reproduce this thing, or this thing, you see that this metric has to have this form, eta mu nu is equal to 1 0 0 0. There are 4 things: 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. Okay, why do I choose it like this? Because I want to reproduce this thing. Okay, so if you for example, you see that eta mu nu also has this property, only the diagonal components are non-zero. All non-diagonal components are 0. So if you make the summation and take the non-diagonal components, it will be 0. So the only term surviving in this would be a0 b0 eta 0 0 plus a1 b1 eta 1 1 plus a2 b2 eta 2 2 plus a3 b3 sorry, eta 3, 3, right? These are the only terms that will survive. Am I right? Okay. Now, if you know the value of eta 0, 0, eta 1, 1, okay, this is eta 0, 0, this is eta 1, 1, eta 2, 2, and eta 3, 3. You see that substituting this, you will get a0, b0 minus a1, b1 minus a2, b2 minus a3, b3. You see, it's exactly this. It's exactly this, right? So we can obtain this. Okay, so we can obtain this form by simply saying that the metric of Minkowski space is eta mu nu, given by only the diagonal components. This is one way to write. I'm writing the diagonal components 1, minus 1, minus 1, minus 1. Okay. So, and it's the metric actually summarizes the geometry. Right? The metric gives you the geometry of a given space. All right. So this is the metric for Minkowski geometry. We know that for Euclidean geometry, the metric was 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. The word is metric, not matrix. It's metric. Okay. Because it tells you how to measure the length between 2 points. All right. So finally, we can write this ds square. We already wrote it as c square dt square minus dx1 square minus dx2 square minus dx3 square. Okay, we can write now this as dx mu eta mu. Okay, this is a compact way of writing this ds square. Okay, is fine. Following?
Yes, sir.
Okay, good. Now there's another compact notation. You might already be familiar with this. We can, there's an idea called raising and lowering of indices. Okay. And lowering of indices. Okay. This thing can be written as, we can write dx nu eta mu nu, simply this nu is summed over, we can write it as dx mu, right? Or simply, if you have a vector a mu eta mu nu, can be written as a nu, right? We can see the summation of this. All right, we can just expand this thing. I'll explain what this means. Okay, this is known as a one form or a covector or a covariant vector. Okay, this is known as a vector or a contravariant vector, usually it's called in old notation. Now we call this as just as a vector with upper index, right? With the lower index, we call it as a covector or one form. Okay, what does this mean? Okay, why do we do this? Okay, if you look at this, you see that if you look at these components, okay, I'll write it like this. Okay, I'll write it like this. A dot B for vector, it can be written as a mu B nu eta mu nu. Okay, now this you can write as a mu B mu. Okay, it's a compact way of writing it. And what is B mu? Where B mu is equal to B nu eta mu nu. Right, this is scalar product. You can write it like this. Okay, what do you mean by this? What do you see that this nu is summed over, right? So let's check this part. Okay, let's look at this B nu eta mu nu. Okay, what is this? We know that this is equal to B0 eta mu 0, okay, plus B0 eta mu 1. You are summing over nu. Okay, sorry, that's not enough place here. Okay, let me write it here. B nu eta mu nu is equal to, we can write the summation B0 eta mu 0 plus B1 eta mu 1 plus B2 eta mu 2 plus B3 eta mu 3. Okay, but we know that only one of these terms will survive, right? Where if mu equal to 0, it will be this term. If mu is 1, it will be this term. If mu is 2, it will be this term. If mu is 3, it's this term. You see that this we define it as B mu. It has only one index. Okay. Now, what are these components? What are these components? For example, if you take B0, okay, if you take B0, right, you just make the summation, but you are substituting mu by 0. Right? This would be B nu eta mu 0, and you sum of B nu eta 0 nu, and you sum over nu, but only one term will survive. This is equal to B0 eta 0 0. All other terms are 0. Am I right? Okay, and what is this? You see that B0 is equal to B0. It's the same number. Okay, it's the same number because eta 0 0 is plus 1. Okay, in the convention of the metric that we have chosen. What about the space part? Right, I'll write it as B1, for example. If you take B, if you need B1, you write it as B nu eta. See, if I put 1 here, you put 1 also here. Okay, eta 1 nu, you just sum this, and the only non-zero term is for nu equal to 1. Am I right? Because all diagonal terms are 0. This is B0, so this is 0 plus B1 eta 1 1. Okay, and what's eta 1 1? If you look at the matrix, you see that eta 1 1 is minus 1. So you see that B1 is equal to minus B1. Okay, B1 is equal to minus 1. Similarly, you'll see that B2 is equal to minus B2. B3 is equal to minus B3. Okay, by this notation. What does this mean? When you lower the index, the space part get an extra minus sign. Okay, whereas the time part, it remains the same. Time part remains the same. Right? Now let's just expand. A mu, B mu, this is equal to A0, B0 plus A1, B1 plus A2, B2 plus A3, B3. Okay, but what is B0? B0 is equal to the upper index B0. But what is B1? We already found that B1 is equal to minus of B1. Okay, minus A1, B1 minus A2, because B2 is equal to minus of B2. Okay, A2, B2 minus A3, B3. And this is exactly the scalar product that we obtained earlier, right? You see that this is exactly the scalar product that we obtained earlier. So this is a compact notation for obtaining scalar product. Okay, you can always write A dot B, you can write it as A mu B nu eta mu nu. You can also write it as A mu B mu. Okay, and both this will give you the same thing, A0 B0 minus A1 B1 minus A2 B2 minus A3 B3. Okay, fine.
Yes, sir.
All right. Are there any questions regarding this? Okay, we are doing all this to define what we know as the momentum for a vector. That's what we'll be using in what do you say, in solving problems. Okay. So let's just look at the examples of a vector. I'll just conclude after this. Okay. A simple example is x itself, x mu. Okay, or we can call it as x vector. It has components x mu. It has components x mu is equal to, okay, this is a vector without a vector sign. It has components x0, x1, x2, x3, or we can write it as x0. Sorry, x0 is ct. Okay, you can also write it as ct, comma x1, x2, x3. Right? And if you take lower the index, x mu, this is a vector and this is a covector. Okay, this is known as a vector and this is known as a covector. Okay, actually we use these things in this basic geometric idea in many places. Okay, so x mu is the space component remains the same, but it is minus x1 minus x2 minus x3. Okay. This is the position. You can call this as the position for vector if you like. This is the position for vector. Okay. So once you write the position for vector, immediately you may think of writing what's known as the velocity for vector. Okay, you want to define a velocity for vector. How do you define a velocity for vector? Okay, I think we'll do that in the next class. Okay. I'll give you a hint. You could actually do dx mu by dt. Okay, you could actually try dx mu by dt. Okay, but does this transform as a vector? For vector? Does this transform as a for vector? The answer is no. Why? Because x mu, dx mu transforms as a for vector. The numerator transforms as a for vector, but the denominator also has a non-trivial transform because time is the same. Okay, time remains the same. Time does not remain the same. Time changes under Lorentz transformation. So numerator and denominator have transformation. So this does not transform according to the Lorentz transformation. Okay, what could we do in order to construct a velocity for vector? We know already that the numerator transforms like a for vector. Okay, so we need below here we need a quantity that is invariant under transformations. Okay, that looks like that, and we know already that proper time. We already have discussed that proper time is invariant under Lorentz transformations. Okay, so the immediate choice for velocity for vector is this. We'll call it as eta mu. Okay, it's not dx mu by dt, but it's dx mu by d tau. Okay, now you can easily see that this transforms like a for vector because the transformation property of the right hand side, the numerator transforms like a for vector. We know that this is a for vector. This is an example for a for vector, like a for vector. Okay, whereas the denominator, right, it's invariant under Lorentz transformation. All right, so this whole thing transforms this like a for vector. Okay, so we can say that eta mu prime, the transformation property can be written as eta mu prime is equal to lambda mu prime nu eta nu. This transformation property is satisfied by this particular combination. If you take dx mu by d tau with d tau property, but this transformation property is not satisfied by this combination. Right, so this is known as the velocity for vector. We'll look at the components of this in the next class, but I'll just give you another thing. We can also define a momentum for vector. Momentum for vector by just this. All right, we'll define it like this: p mu is equal to m multiplied by eta mu. Right, in Newtonian, we already know that p is equal to mv, where v is a 3 vector and mv is also a 3 vector. Okay, here for vector you just do the same thing. You take the for velocity and multiply it by the mass. Okay, and mass is an invariant quantity, so this also transforms just like a for vector. All right, you'll see that p mu prime is equal to lambda mu prime nu p nu. Okay, one more thing. All right, we already have said this. All right, scalar product will be using this of 4 vectors is Lorentz invariant. Right, this is an important thing that you have to remember. Okay, so next class we'll just discuss this velocity for vector and momentum for vector in more detail, and we'll also make use of the idea that scalar product of for vector is a Lorentz invariant quantity, and then we can use this to solve problems. Okay, we can use this to solve these basic ideas. All right, this momentum for vector, we can use the momentum for vector because we'll see that it's a conserved quantity. Okay, momentum for vector, and the fact that the scalar products of 4 vectors are Lorentz invariant. All right, we can use these two properties, okay, these two ideas to solve problems. Okay, especially this problems involving high energy collisions. All right, high energy collisions. You'll see that this is a very easy. This provides a very easy way of solving problems. All right, we'll discuss these things in the next class. Okay, are there any questions now? So this is all very brief and quick, but I hope you are following somewhat. If you have any doubt, you can ask. These concepts will become more clear as we solve more problems. Okay.